Welcome back to Pratik Academy. In last video, we have seen methods for analysis of vibrating systems, that is Newton's method, energy method, and Rayleigh's method for transverse vibrations, longitudinal vibrations, and or longitudinal vibrations, transverse vibrations, and torsional vibrations. Sorry. Then in this video, we will solve some sample numericals for on that systems. So let's start. So first take formulas for these systems. This is mx double dot plus kx is equal to 0. This is equation for longitudinal system. In here natural frequency in radian, remember natural frequency in radian is equal to 1 root k by m, and if they are asked in hertz, then we have to divide it by 2 pi. Then equation becomes 1 upon 2 pi 1 root k by m. Hertz means revolutions per second. Okay, and if they are asked in revolution per minute, then we have to multiply it by 60. Okay, for converting revolution per second to revolution per minute. Then theta double dot plus kt upon I theta is equal to 0. This is equation for torsional system. Then natural frequency in radian, here again it is in radian, will be under root kt upon I. Kt is a torsional stiffness of rod. I is the mass moment of inertia of our rotor. Okay, then theta double dot plus g upon L theta is equal to 0. This is equation for transverse system. Then natural frequency in radian per second is equal to under root g upon L. This is radian per second here, sorry. Then when we attach mass to spring, then its spring deflects by some initial amount, that is static deflection is equal balanced by weight. From this equation we get k by m is equal to g by delta st. Then k by m is nothing but natural frequency square. So under root g upon delta st is another formula for natural frequency for spring mass systems. Okay. Then by Newton's method we have accelerating torque is equal to restoring torque, or accelerating force is equal to restoring force. Then next is a by energy method, total energy at any instant is constant. Then by Rayleigh's method we have maximum kinetic energy at mean or equilibrium position, mean position is equal to maximum potential energy at extreme position. Then these are two arrangements. First see these arrangements. So there is a concept of equivalent spring. This is most important concept. There are, suppose we have a system where springs are there are numbers of springs arranged one by one and connected to one another on. Then there are two methods in which they are connected. One is series and one is parallel. So this is parallel arrangement and this is series arrangement. In parallel arrangement, one end of each spring is attached to support and another end is attached to mass. Then this system is called as parallel system. In series, one end of one spring is attached to support and second its another end is attached to second spring. Okay, so here is only one spring is connected to support and another end is connected to this first spring. So this arrangement is called series arrangement. Okay, now similar to our sum, when we applied force on this system, then force on this spring and this spring will be equal. Okay, total force is sum of forces acting on this spring and this spring. So F is equal to F1 plus F2 here. Okay, when arrangement is in parallel, but when we deflect this mass by amount say x, then here also deflection is x, here also deflection is x. So deflection is same here. Here in case of series, when we deflect applied some force, then this force will be equally applied on first spring and second spring, but total deflection of spring is sum of deflection of each spring. Then what is equivalent spring? Equivalent spring is a single spring here having stiffness Ke. It is equivalent stiffness which will represent our total system. Okay, it is a spring having stiffness which will represent our total system. It is here deflection in this system will be equal to deflection in this system. Here again in series it is equivalent spring, means spring which will give same effect as that of our total system. So suppose we have applied force F here, then total force is divided in two parts, F1 plus F2. And then first spring force will be K1x, in second it will be K2x. So total force is K1x plus K2x. Deformation is same. Then we have applied same force here and there will be again same deflection. Then it will be Ke into x for equivalent spring. Cancelling common terms, we get equivalent stiffness is equal to sum of stiffness of each spring in system. So Ke is equal to K1 plus K2. This is for parallel arrangement. Okay. When springs are in series, then suppose del is a deformation of system here, total deformation of system, then it is sum of del 1 plus del 2. It is deformation in each spring. If we replace this spring by one spring which is giving same deflection by applying same force, then here our d will be here, as we know that F is equal to K into del. So in case of first spring, F is equal to K1 del 1, so del 1 is F upon K. Similarly delta will be F upon K2, and here del equivalent here will be F upon K. Then cancelling common terms, we get 1 upon Ke is equal to 1 upon K1 plus 1 upon K2. So this is for parallel arrangements. Okay. Then note on one important point: when we reduce length of spring by its half, then its stiffness is increased by twice. Okay. This is important relation required in some numericals. When we reduce spring length by half, then its stiffness is increased by twice. Okay. For here in parallel arrangement we have take K is sum of stiffness of individual spring. Here total force is divided into each spring, and total deformation is equivalent to deformation in each spring. This del is equal to del 1 is equal to del 2, and F is equal to F1 plus F2 here. Then in case of series, 1 upon Ke is equal to 1 upon K1 plus 1 upon K2. Total force is same acting on each element. Total deformation or equivalent deformation is sum of deformation in each spring. Then this is the relation spring force is equal to Kx. Okay. If you consider restoring force for torsional system, then it will be Kt into theta, torsional stiffness into angular displacement. Okay. Next is strain energy. Strain energy in linear will be 1 by 2 kx square. In case of angular it will be 1/2 kt into theta square. Then kt, torsional stiffness per unit deformation or angular deformation, that is torque per unit deformation, is equal to Cj on L. This is from our torsional equation. So these are the some important formulas. Now we will solve some numericals based on for purpose of understanding. We have divided this content of these numericals in 3 videos. In this video we will see few examples, and in next two videos we'll see rest of examples. So let's see here our first example. Here problem statement is an unknown weight W is attached to unknown spring K. It gives natural frequency 89 rpm. So frequency is in rpm. When 50 Newton weight is attached to system, frequency reduced to 75 rpm. Determine W and K. Okay, so here given system is spring mass system and given is a natural frequency. So we have natural frequency given is in rpm. Okay, but we have for rps f1, that is natural frequency, is equal to 1 upon 2 pi under root k1 upon m1 for first case. This is in hertz or revolution per second. Given frequencies in rpm, so divide it by 60 to convert it into rps. So we have converted here. So 89 upon 60 is equal to 1 upon 2 pi under root k1. Given is the weight. Okay, given is a weight, so we have converted it into mass by dividing by g. So this is the first. In case 2, same spring is there, but its frequency is reduced to 75 rpm. It is 75 by 60 hertz. When weight is attached, increased by 50 newton. So total weight will be W plus 50 newton. Converting to mass, we have divided total by g. Then taking ratio, we will get here W. Okay, in taking ratio we will get here equation 89 by 75 is equal to under root W plus 50 upon W. In solving this equation, get W will be equal to 122.49 newton. Okay. Then next is they have asked, okay, it is spring stiffness. For that purpose, put this value in either equation 1 or equation 2. Putting in equation 1, we get K, that is spring stiffness, is equal to 110.62 Newton per meter. This is the first example. Okay. So let's see another example. Here problem is calculate natural frequency for torsional pendulum for given data. Length 1 meter, diameter of rod 0.5 centimeter, diameter of rotor 0.2 meter, mass given is 2 kg, mass of rotor is this, and G, that is torsional rigidity of rod. C or G is 0.83 into 10 raised to 11 Newton per meter square or Pascal. Then for torsional system, we have natural frequency is equal to under root kt upon I. Okay. I is mass moment of inertia for rotor, so I is equal to m r square by 2. This r is radius of rotor, not of rod. So diameter of rotor is given 0.2, so its radius will be 0.2 divided by 2. Formula will be mr square, so 2 into 0.2 divided by 2 is to 2. So I is equal to 0.01 kg to meter square. This is the I. We have calculated I. Then kt is torsional stiffness, that is torque per unit deformation. And we have relation c theta or g theta upon L is equal to tau upon J. So torque per unit deformation will be gj upon L. So g given, length of rod given, and formula for J of rod will be pi by 32 d raised to 4. Then putting this is d is diameter of rod, they have given in centimeter, convert it into meter. For that purpose, multiply it by 10 raised to minus 2, we will get this 0.005 raised to 4. Okay, in solving this, we get torque per unit deformation is equal to 0.59 Newton meter per radian. This is kt. In putting these values, we will directly get natural frequency in radian per second as 29 22.6 and divided by 2 pi, you will get frequency in hertz, that is revolutions per second, 36 revolutions per second. Okay, so these are two numericals we have seen formulas. In next video we will see rest three numericals, and in another video we will see remaining numericals. If you have any doubts, you can contact us. If you like this video, please share, subscribe our channel. Thank you.